అందరికీ నమస్కారములు. నమో నమః. గురుభ్యో నమః. Today is the last day of our classes on Vedic mathematics. So we had 4 exciting sessions, interactive sessions with Gautham ji. Today we are going to have the last one. We will start the session with Vande Mataram by Challa Chittibabu garu and Prarthana by Ramesh ji. Challa Chittibabu garu, please.
Vande Mataram, Vande Mataram, Sujalam Sufalam, Malayaj Sitalam, Sasya Syamalam Mataram, Vande Mataram. Subrajosna pulakitayaminim pullakusumita drumadala shobhinim suhasinim sumadhura bhashinim sukhadam varadam mataram Vande Mataram. Vande Mataram.
వందే మాతరం. ధన్యవాదములండి చల్లా చిట్టిబాబు గారు. Now let us request Ramesh ji to chant Prarthana, please.
Sure. Harihi Om. Sarvebhyo Namo Namaha. As usual, let's start with meditation for a minute and then let's recite Omkara for 3 times. Then I'll do the Prarthana. Om Gananam Tva Ganapatikum Havamahe Kavim Kavinamupamastravasthavam Jeshtarajam Brahmanan Brahmanaspata Anasnunvannutabhissidasadanam Om Sri Mahaganadhipataye Namaha Om Prano Devi Saraswati Vajebhirvajadimati Dhinamatiryavatu Om Sri Mahasaraswatye Namaha Gurureva Gati Gurumeva Bhaje Gurunaiva Sahasmi Namo Gurave Na Guru Paramam Sisurasmi Guroho Matirasti Guru Mam Pahi Guru Jnananandamayam Devam Nirmalaspatikakrutim Adharam Sarvavidyanam Hayagrivamupaasmahe Smriti Smriti Purananam Alayam Karunalayam Namami Bhagavatpada Sankaram Loka Sankaram शङ्करं शङ्कराचार्यं केशवं बादरायणं सूत्रभाष्यकृतौ वन्दे भगवन्तौ पुनः पुनः ईश्वरो गुरुरात्मेति मूर्तिभेदविभागिने व्योमवद्व्याप्तदेहाय दक्षिणामूर्तये नमः असतो मा सद्गमय तमसो मा ज्योतिर्गमय मृत्योर्मा अमृतङ्गमय ॐ शान्ति शान्ति शान्तिः मातृदेवो भव पितृदेवो भव आचार्यदेवो भव अतिथिदेवो भव ॐ सहना भवतु सहनो भुनक्तु सह वीर्यं करवावहै तेजस्विनावधीतमस्तु मा विद्विषावहै ॐ शान्ति शान्ति शान्तिः स्वस्ति
ధన్యవాదములండి రమేష్ గారు. Thank you so much. Now let us request our Guruji, Gautham ji, to start the webinar, please.
Sarvabhyo Namo Namaha. I'm just starting the presentation. Now, first let me show you that one paper that I referred actually, that Urdhva Tirjagabhyam is the most efficient way of multiplication, and that if it is multiplied, imagine there are billions of devices throughout the world, and each of them in the each cycle, so they design the circuit in different format. So this, they prove that by doing so, they are getting that some few delay in nanoseconds. There is some saving of time in each cycle. That means power requirement is less if you use instead of conventional multiplication, if you use the Vedic multiplication of Urdhva Tirjagabhyam. And that paper, the initial paper, I will show you. That is this paper by Ganesh Kumar and Karishma. Design of high-speed Vedic multiplier using Vedic mathematics techniques. So there you find that that day I covered the session of Urdhva Tirjagabhyam. But these kind of things, actually, this particular table, maybe that I will share the paper in the with Colonel Sahib, and then he can circulate it. So those who are interested can go through that. Here, actually, this I am telling that 5498 was being multiplied with 2314, and then 4 into 8, 32. So 2 is written here, unit digit and 10 digits. And unit digit, everywhere unit digit is in the lower part, 10 digit is in the higher part. So when we add them, it gives a result. This is exactly like Urdhva Tirjagabhyam. Here everything is written in front of you, so that anytime you can verify any of the things. If anywhere any mistake, then you can do it. But with practice, this whole thing can be in the summed in the memory and then put it. That is the main idea. With slightly more brain power, it is possible to make it in the memory. Now I stop sharing this, and then I will come to. I came back to my presentation. I was here, or I found that actually we covered both the positive and negative thing coming from the binomial expansions. Positive way, where we 10 times the remainder, we 10 times the remainder, we add the quotient to the 10 times of remainder in case of positive method. Whereas in a negative method, because we found that if it is something is ending in 1 and it requires multiplication of 9 in to use the positive method, multiplication of 9 both in numerator and denominator, it makes it very huge. So we went for a negative method. Actually, it is a binomial expansion of 1 by 10n plus 1, like 21, 31, and so on. N is equal to 2, 3, and so on. So here we found that there is alternative plus and minus, but actually if we do this expression like this, everywhere we found that 10n, that 10 times the remainder, quotient should be subtracted from that 10 times of the remainder. That is the idea in this symbol minus means. So we did it like that. But in case of 121, what happened? There we got some this point minus 5. Minus 5 we got, and because of which we got this minus 5. We got the minus 5, this one. Because of which there is a particular consideration has to be put that oh, you got this minus 5 here. And we found that this expression is, we do it, and so that this, remember that quotient can be negative, but remainder is not negative. Remainder will be always positive. Remainder will be always positive. You always remember this. So we would not have done it minus 2 into 2. We should not have written minus 2 into 2 minus 1. It is not. Minus 3 into 2 plus 1. So this is actually, when we divided that, it became minus 3. So therefore, this vinculum came. So that is the only thing that we have to handle properly, these minus things. So that was the challenge. But first we started with a example where there was no minus. Some cases there cannot be minus, but if you understand, it is good that how you are doing it. Instead of 20 plus 3, you do 20 minus 3, 10 minus 4, 20 minus 1. That way we went and came back to here. So that was the case of this negative method. We covered that in case of 7, you can have both the choice. If we are 1% with the negative method, you do it. Otherwise, you continue the positive method. It will not be very big. It will not be as big as multiplied by 9. So here, some of you must have done this thing. Yesterday, we are given the exercises. Now yesterday I required to be stopped. So I continue with this one, that what is the periodicity? Periodicity, how it comes. Sometimes 31, we got the, 29, you got the periodicity of 28. 31, you get it 15. And 41, you got only 5. Why it is so? It is because this way. Periodicity or the length of the recurring part in decimal depends upon the denominator, like 41 is denominator, or say 29 is denominator. Denominator being a factor of repeat 9. There is a concept of repeat 9 numbers of minimum length. That is minimum of 9, 99, 999, etc. Something is factor of 9. Obviously, it will be factor of 99 also. It will be factor of 999 also. But its repeatability will what happen? Repeatability will be on the first digit, 1 digit. For example, denominator d is equal to 3 has periodicity to 1 because 3 is a factor of 9. The number 3 also factors of 99, but 9 is the minimum of all. D is equal to 11. Something by 11 has periodicity 2 because 11 is a factor of 99, but it is not factor of 9. So it is minimum is 99. Now denominator 27, denominator 37 has periodicity 3 because it has factor of 999. You know that 37 into 3 is 111. And obviously, again 37 into 27 becomes 999. So 27 also has this. 27 into 37 is 999. So 41 has periodicity 9 because it actually factor of 9999 because 41 into 271 into 9 is this number 9999. Now all these numbers 7, 13, 21, 39, 60, there are not many because those are actually very basic, those prime numbers, and their factors are many, their multipliers are many. So all these have periodicity 6, all being a factor of this 6 numbers of 9 called repeat 9 of 6. Now here I get a full order like this, full periodicity table chart. So here we found that these 3 periodicity 1 or 3, 11 has periodicity 2, this 37 and 27 has periodicity 3, periodicity 4 is having only 1, this 101. Actually, why I am putting the prime number only. For example, suppose we put a number something by 303. Obviously, that also will have periodicity 4 because it contains that. It will be also a factor of 9999. Now this periodicity 5, 41, 271, and obviously 3 times of 41 is 1, 2, 3. That also will have periodicity 5. These all numbers are periodicity 6. These actually some of them are prime and some of them are composite also. Like 63 is composite. 21 is also composite. So 7 into 9 is 63. 117 is actually 13 into 9 is 107. So 7 periodicity, 239 and 46, like that way. 8 periodicity, 9 periodicity, and 10 periodicity, and so on. It comes like that. So here we get, see, 19. 19 came here because it is a factor of 18 numbers of 9. This actually expression I am putting here, 10 to the power 18 minus 1 is actually 18 numbers of 9. So because of that, its periodicity is 18. Very first one we evaluated, this 19, 1 by 19, anything by 19 has periodicity 18. So this is the chart, and this there is a slight analysis on that about this relevant R or H numbers. Here R stands for repeat 9 numbers, and H stands for hollow numbers. And hollow number is defined, I'll tell you, R with a suffix n will stand for n numbers of 9s. That means R5 is 9999. Here it's R5. R5 is coming here. Is 9999, and 41 is a factor of that. H with suffix n will stand for 1 followed by n minus 1 number of zeros and followed by 1. Like H5 will have actually like this. Actually, it is actually 10 to the power 5 plus 1. 10 to the power 5 plus 1 is H5. So these are the numbers, because a R number with even suffix is a product of H and R with its half suffix. Thus, the deciding factor becomes with H, as the factor of R is already considered earlier. Suppose I'll explain this. Suppose so 1 or say 9, I'll tell you 999. Okay, this actually is equal to 999 into 1 0 0 0 1 999. So this is equal to R6. We call it R6. So this is R3, triple line. This is R3. Oh, sorry, R3. And this is 10 to the power no, I'm sorry. 100. So this is H3. H3 is how much? So if you 1001, if you multiply with 999, it will be 999999. Okay. So R3 and so it is 1001 R3. Sorry, H3. So this 1001 has factor of 7 and 13. 7 and 13 into 11 is equal to 1001. So that's why this 7 and 13 has periodicity 6. It is not coming from factor of 999. This 999 contains factor of 37 and 27. These are already taken care of. Periodicity 3, but periodicity 6 is coming from being factor of 1001 H3. That's what you just think of that. Those of mathematical intent can enjoy this part. Why I told that this particular analysis. Anyway, that was the small part. This remaining thing was there from yesterday's. Now today I will cover the divisibility rules. Okay. Now divisibility without actual division. You can divide always and then you can find that. But without actual division, just by observation, we can do something is divisible by another thing or not. The numbers 2 and 5 being factors of 10, that base is 10. So 2 and 5 factors of 10. We have similar rules for 2 and 5. Like divisibility by 2 to the power n requires last n digits to be divisible by 2 to the power n. Like, for example, you know that 2 to the power 1 means 2. If the last digit of a number, which is called even numbers, those are all divisible by 2 because last number is divisible by 2. So similarly, if it is 2 digits, last 2 digits have to be judged for 4. If last 2 digits are divisible by 4, then it will be the whole number will be divisible by 4. Whatever remains earlier doesn't matter. Similarly, divisibility by 5 to the power n requires last n digits to be divisible by 5 to the power n. Achha, what will happen if in case of suppose divisibility by 8? Can anybody tell? Divisibility by 8 will be required that suppose we do something like that. Say 128. So whatever bit is, suppose 7, 9, 8, 7, big number is there. And I found that 128 is divisible by 8. So therefore, all numbers will be divisible by 8 because it is 2 to the power 2 cube. So three digits, last 3 digits have to be considered. I didn't cover that, but I just extend that way. Divisibility by 5 to the power n requires last n digits to be divisible by 5 to the power n. That is, this number is divisible by 25. Since 75 is divisible by 25, etc. So, and last number 5 or 0 means divisible by 5, we already know. Divisibility by a composite number demands divisibility by its factors. That is, 42 is divisible by 6, as it is divisible by 2, as well as by 3, so it is divisible by 6. 135 is divisible by 15 because it is divisible by both 3 and 5. That is about the composite number. Now, divisibility by divisor ending in 1, 3, 7, and 9. You remember this number. Earlier also we did in another context, in context of the recurring decimal. This has general method called osculation. This is the Vedic method of osculation. This is Vedic method called osculation, which gets a trivial form in case of 3, 9, and 11 because osculator will find osculator is +1 for 3 and 9 and -1 for 11. So we do not notice. There is another procedure as if we do not learn as oscillation method, but still we can manage with this plus and minus because it is so trivial kind of thing. So, but therefore, I tell you, from childhood we learn all these things. But we skip what? We skip 7 divided by 7. We skip 7 divided by 13, 17, 19. All these numbers we skip the divisibility. Although they are also as easy. Only thing is that we have to mind it that instead of +1 or -1, there may be -2 sometimes, +2 sometimes, and so on. +5 sometimes. Divisible by 3. These are trivial form, as I told. A number is divisible by 3 if the sum of all digits is divisible by 3. For example, the number this is divisible by 3 because the sum of its digits, that is, if we add all these numbers, become 24. And 24 is divisible by 3, so therefore this whole number is divisible by 3. Divisible by 9. A number is divisible by 9 if the sum of all its digits, make the sum of all the digits. And if it is found that it is divisible, it is this sum of all the divisions is 27, and 27 is divisible by 9, so the whole number is divisible by 9. So that we have learned from our childhood. Divisibility by 11 is number is divisible by 11 if the difference of sum of alternative digits, say even and odd position digits, is either 0 or divisible by 11. For example, the number this is divisible by 11 because this on one side we add the alternative number 9, 4, 7, and other side we would try alternative numbers like this, and this becomes 11. So it is divisible by 11. It could be 0 also. It could have been same. So it could have been same also. So this sum, odd sum and even sum could have been same, and the result could have been 0. Then also it will be divisible by 11. 11 itself, see, is a odd position 1, 11 position 1. So 1 minus 1 is 0, and the 11 is divisible by 11. It's like 33 is divisible by 11 because 3 minus 3 is 0. 3 minus 3 is even position, odd position, 0. Exercise. Find whether the number this is divisible by 3, 9, and 11. Anyway, that we can do. Now, oscillation method. A 2 or more number digit integers n can be expressed in the form 10r plus u. Actually, I will tell you the procedure first, and then algebra I will not cover much. You can see those are interested. So this any big number can be expressed in the form rest of the digits 10r plus 1. Like say for example, I write say 753 is equal to what? 775 into 10. I do not write the full expression like 7 into 100 plus 5 into 10 plus 3. Only this much I want. So rest of the digits into 10 plus 3. It can be anything. That can be 875. It doesn't matter here also. 875 into 10 plus 3. So 10 are rest of the digits and unit digits. So unit digits and rest of the digits comprising of 10 digits and beyond. Oscillation is a basic method to create a smaller number, smaller integer, t, test integer, you can say, and r plus mu. That m is called the oscillator. So we have to find the oscillator in this case. It is being said that the integer capital N is oscillated by the factor small m to get the test integer t. The process can be recursive with the same oscillator m. That is the unit digits of t. Again, the t will have a unit digit and rest digits. So again, you do another, suppose it is called t1. Then t1 will have is equal to 10 into r1 plus that u1 So this, when you say that I do R1 plus M times U1, that will be my T2, the second order of test digits. So it can be recursive. Recursively, we will apply that so that the unit digits T can be multiplied by M and rest, added to rest digits of T to get the next T. Osculation is an efficient method for testing divisibility by divisors ending in 1379. It is a matter to determine the required M given by a capital N and a divisor D ending in 1379. The oscillator M can be found with following consideration. Here actually slight thing is there. They given a divisor D. Number N is not required. For divisor D, there will particular. I'll change it. This given a divisor D. So oscillator M can be for consideration. So this is actually algebra is there. So I'll tell you the procedure only. See, algebra is there. So the algebra is not very difficult. So it can be found out. Those of you who are interested in algebra, this can be done. So now I directly jump towards the procedure. Those of you who are interested in algebra can discuss separately. Let's test whether the 343 is divisible by 7 or not. First, we find the oscillator for 7. We see that 10 into 5 minus 1 is 49, which is divisible by 7. So what we can do, anything end in 7, we can always make it 7. Actually, you have to, again, the same thing as the previous one. Something you have to find that it is ending in 9. Because something is ending in 9, then only I can express it as some multiplication into 10 minus 1. Okay. Is that clear? So therefore, not this 4, but this 5 becomes my, not this 7. I mean, not this 7 by which we multiplied that, but by this 5 becomes my oscillator. So in case of 7, 5 is oscillator. Then how will we apply that? The 343, I'll go to the next step. It is actually, this is say the whole number. This is the rest of the number, 34. And this is the unit digit, 3 is unit. I cut it like this. Separate the unit digit. So unit into the oscillator, MU here, U into M is equal to 49. Came back to comes to 49, which is manageable. Which is actually you can directly get it transparent. That is manageable. Again, you do suppose 9 into 5 plus 4, it will be again come back to 49. So it doesn't matter how many times. So it will already 49 is the it is divisible by 7. So therefore 343 also divisible by 7. I take a bigger number. So take this. Take this number. I separate it out. So this, I mean, I separate it out like this. And 6472 and plus 4 into 5. This is the unit digit into M. This is oscillator. This is the rest digit. So this becomes 6492. Again, I separate it 649 plus 2 into 5, 659. Again 65, this also 65 plus 9 into 5 becomes 110. 11, again 11 into 0 into 5 is equal to 11. Not divisible by 7. So by backtracking, all these numbers are not divisible by 7. Suppose had we gotten this something 7 or something like that, So all the backtracking would have been all divided by 7 would have been. Now test the divisibility of this thing by 13. Now again, first have to do what is the oscillator for 13? For anything ending in 3, we have to multiply it by 3 to get something ending in 9. Because ending in 9, if we get ending in 9, then only I can put it something multiplied by 10 and subtract 1. That is the expression, that is the algebra requirement. So 4 becomes my oscillator is in case of 13. So 10 into 4, that is 39 is divisible by 13. So m is equal to 4 for 13. We do, this is given. This number is divisible by 13 or not. So 1163 plus 5 into 4, this is my oscillator. 1183. Then 100 again, I cut it. 118 plus 3 into 4 is 130. Again, we do it. 13 plus 10 into 4 is 13 itself. So that means, therefore, 13, 130. In fact, it could have stopped here itself. Sometimes ending in 0, and you need not do it because you know that it is not divisible by. Divisibility doesn't depend upon the presence of 0, so it will be divisible by. Obviously, it will be only have to consider if something is 0, don't do it. See, this just to is shown just to have a completeness, but it's not required. If 13 means actually it is divisible by 13. 130 means. So these are all this backtracking, all these numbers are divisible by 13. Test divisibility of this by 23. This number by 23. Again 23. What happened? You will find some similarity with the case of recurring decimal, because here also I'm finding something ending in like 23 recurring decimal. Earlier we multiplied by 3, you remember? And we did divided by 6, divided by 7 always, something by 7, 7, 7. So it came, it was recurring decimal with something by 23. So similarly here also, we multiplied by 3 to get 69, and which is 10 into 7 minus 1. So we got the this oscillator for 23 is 7. Oscillator for oscillator is 7. So here we do 7. We always similarly we did 7. Always cut the unit digits, separate it out, then do it. Finally come to 92, and 92 is equal to, again we can, if you do it exactly came to 92 itself, we can found that okay, 92 is 4 times 23. The small numbers you may know, you can stop there itself, or you can, if you are not satisfied, you can continue with this one and found to that. All these numbers are backtracking, all the numbers are divisible by 23. Hint: multiply numbers ending in 3 and 7 by 3 and 7 respectively to get oscillator. That is 17 into 17. 12 is the oscillator for. So it is the hint. Positive, negative, and minimum oscillator. If 10m plus 1 is divisible by d, all the algebra considerations hold good for oscillator minus m. Like T should be calculated as R minus mu. So that the same algebra will hold here. So the oscillator of with minimum absolute value is called minimum oscillator, and most suitably chosen to get test divisibility. Suppose, now here we come. Here we say that 19. How to get the oscillator of 19? Oscillator of 19 is how much? Now you
2.
I require some
Three,
reaction
three,
so that
three,
I understood that
seven.
I understand that people are following me.
3
What
into
is the
7 minus
oscillator of
1?
19?
7 into 3 minus 1. So maybe 3 is the oscillator. 7 into 3. Oh no, minus 2. Sorry.
10 into 2 minus 1. So 2.
Exactly. This is this. Thank you very much. So it is so that so you have followed nicely. It's fine. Very good. So it is obviously anything ending in 9. Again, that thing of ekadikana purvena. There is some similarity with the recurring decimal and this divisibility. So anything ending in 9. So for 29, the oscillator will be 3. Ekadikana purvena is the oscillator in case of ending in 9. So suppose I use my calculator to get a number divisibility by 9 and find it. Then I'll tell you how to do it. If we get a positive answer, you find satisfied. That's all. Otherwise, I could have taken any random number. Okay. This number 14991. You tell me what is how to proceed for testing divisibility with 19. It's 19. What is the next step? Oscillator for 19 is
140.
oscillator is
1499.
So 1499
Plus 2.
Plus
plus
1 into 2. Yeah.
1 into 2. So is equal to
1501.
150. Next step
150
150 plus 1 into 2.
150
plus
plus
1 into 2.
1
Yeah.
152. Now those of you remember the table of 19, you will find that 152 is nothing but 8 into 19. Anyway, if you are not satisfied, what you do? Next one, next step. This next step I am putting by arrow, and the calculation I am doing by is equal to. Equal to means I am calculating this, and the arrow means going for next step. So this becomes how much?
15 plus
Then
2 into 2.
15 plus 4, 19.
15 into
2 into 2.
sorry, 15 plus 2 into
2.
Oscillator, isn't it? Is equal to 19. Okay. So that means 19, 152, 1499 and 14991. Everything is divisible by 19. So is it not interesting? So this comes like that, oscillator for acha. Now positive and negative and minimum. Yes. I suppose now I go for to find the oscillator of 21. I want to test the divisibility with 21. What to do? Based upon so far we had learned, we have to multiply by 9 to get. Same thing is happening like that regarding decimal thing. 189. And 189 is 19 into 10 minus 1. So this 21 has oscillator 19. Suppose something is, I want to divisibility by say 63. whether it is divisible by 21 or not, what I do? 6 into 19. Oh, sorry. 6 plus 3 into 19 is equal to comes back 63. Nothing happens. So we have to multiply by 19 always. Suppose had it been something 19 and 9, say 69 I do. So I have to do 9 into 19. So there it must be some other way. So that's what I meant to say. This is called negative oscillator. If 10 m plus 1 is divisible by d, all the algebraic consideration hold good for oscillator minus m. T should be calculated as r minus mu now. In this case, minus m can be called the negative oscillator. The oscillator with minimum absolute value is called minimum oscillator and most suitably chosen to test divisibility. Numbers ending in 3 and 7 have to be multiplied by 7 and 3 respectively to get it, to get the negative oscillator. Example, 7 into 7 is 10 into 5 minus 1 and 7 into 3 is 10 into 2 plus 1 are both divisible by 7. So m is the minimum positive oscillator for positive oscillator and minus 2 is the minimum negative oscillator as well as the minimum oscillator for 7, and that is the most suitable for use. So oscillator 3 and 9, oscillator for 3 and 9 are plus 1 and this is minus 1. That is why they are so trivial. Now test this table of positive and negative oscillator. The positive, say these are so trivial actually. We never noticed that we use oscillator. Simply in case of 3 and 9, what we did? Add up all the numbers. That means unique digit is always multiplied by 1 and then added. Then again multiplied by 1 and added. You do not notice that something is getting multiplied. We simply all added together in case of 3 by 9. And in case of 11, what happened? Unit digit is multiplied by minus 1 and added. So always it is negative of that thing. So we do alternative numbers adding and then subtracting it. It is equivalent to that. So we didn't notice that. So it starts with 2. So in case of the positive, 2 is the oscillator for 19 and minus 2 is for 21. 3 is for 29 and minus 3 for 31. This one. And all the factors, obviously, 13 has this 4. Here also 49 has oscillator 5. Similarly, obviously, is factor 7 also is oscillator 5. 51. 17 will have oscillator minus 5. Okay. Oh, sorry. Yes, minus 5. But actually 17 oscillator would do positive oscillator, then you have to use 12. Because 12 7 are 190. So that way this is that actually table. As the numbers getting higher, sometimes the oscillator will be either positive, negative will be higher, obviously. Cannot help. So negative oscillator. Testing divisibility of this thing by 7. Earlier we did into 5, we did. Now we do 7 into 3 is equal to 21 to 10 into 2 plus 1. So therefore, negative oscillator, we have used minus 2 as the oscillator now. So we do, I can use 5 and add, or you can do into 2 and then subtract. So this one, this also I do this one, I do that way. Should finally come to 77 and divided by 7. So again, if we do, it will not helping much. Sometimes we can make it negative, sometimes 0. So here also you can get 0 also. Therefore, all the numbers are divisible by 7. Note that divisor ending in 1 or 7, it will be easier to use negative oscillator instead of positive oscillator. For example, in case of 21, 10 into 2 plus 1, negative oscillator minus 2, but a positive oscillator is very high. I already repeated this thing. So this is, so in case of 17, it is either this or this. So we can use for divisible by 17. So oscillator can be minus 5 as well as 12. So it is easier to use -5 instead of 12. The criteria of the divisibility using negative oscillator can be either 0 or divisible. It may not be, it may end up 0 also. Like in case of 11, we found that both the things matched. So you using the negative or positive oscillator, you there is a testing here, you can do it. So should I do something more examples? Should I work out more example here?
Yes, sir. Yes, Guruji.
Okay. I take a number 464 721. I want to test whether divisible by 31 or not. Divisible by 31 or not. Now tell me how to proceed.
10 into 3 plus 1.
Yeah. First I do 10 into something plus or minus 1. Both can be possible. So depending upon if it is plus, my oscillator will be negative. If it is minus, then oscillator will be positive. Positive and negative alternate. It is the reverse. So what is my oscillator? Oscillator. What is the oscillator?
-3.
-3. As I told, since this is plus, so this is, the underline will be taken as, so this should be taken as minus. So how do you do? 464 7 2, isn't it? 2 minus 1 into 3. Clear?
46469.
4 6 4 6 9. Next step.
4646 minus 27.
9, 8, 9, 10, 3.
6 minus 9 into 3, 27 is equal to what happens?
4619.
1. Now
461 minus 3 into 9. 9 into
461 minus again
434.
4.
34.
Okay. How much?
43 minus 4 into 3, which is 31.
31. 31.
So that means we got back 31. Here you say, suppose you continue. So it will come to 0 in this case. 3 minus 1 into 3 is equal to 0. If we get 0 or if we get 31, or something divisible by 31, anywhere you can transparent. 31 could have been 62, 93. Anyway, anything transparent, whatever you get, you can stop, or you can end up up to 0. So here, that means that 31, it says 31, then 434, 4646, 46469, this, sorry, 46, not 464, 4619, this, whatever you are getting after equal, this 31, 434, 4619, 46469, and initial 464721, all are divisible by 31. Was it interesting? Was it nice? Understood?
Yes, sir.
Gautam ji, it is interesting.
The divisibility.
But,
Now we come to divisibility by composite number. To test the divisibility by a composite number, we may test divisibility by its factors. Example, now divisibility by 92 and 93. What we do? We find that we test whether 4556 is divisible by 92 or not. Express 92 as 92 into 23 into 4. Now, the number 8556 is divisible by 4 because last two digits, in case of 4, last two digits 56 is divisible by 4. So that part is over. Now, oscillator of, remaining is 23. Now, if suppose somebody, why it is required? Suppose somebody tries to find out the oscillator of 92. It is not possible because it is something 2 and 5 factors are there. It is not possible. Never will find that 10 into something -1 or +1 is divisible by the 92. Never. Because this contains that 2 or 5 factors. This, in case of this is 2. So, whereas 93 you can do it. 93 either you can make it composite, divided into these prime factors, or directly, since it is ending in 3, it can very well, you can find the oscillator and do it. No problem. But here I am showing that how to, even by component level also you can do it. So, in case of 92, there is no other way. You have to do it by separate that 1379 part with the 2 and 5 parts. So it is 23 now. To 23, we know that oscillator is of 23 is 7. So we do it 8556, 855 plus 6 into 7 is 897. And this thing 89 into 877 ultimately it comes back to is divisible by 23. So that means the whole 92 this number is also divisible by 92 because it is divisible by 23 as well as it is divisible by 4. Okay. Now come to whether the same number 8556 is divisible by whether the same number is divisible by 93 or not. So 93 is equal to 3 into 31. So 8556 is divisible by 3 because 8 plus 5 plus this is 24. They have divided by 23. That part is over. Now oscillator of 31 is -3. So we do 8556 that we did already like this, and 37, 39, ultimately 62, which is divisible. Again, you can continue 6 minus 2 into 3, so it is 0. Just for completeness sake, suppose somebody is not satisfied. So 62 is divisible by 31, so this whole thing is divisible by 9. So this is understood. I come to next slide. Now multiplex oscillators. So an n plus 1 higher digit number can be expressed in the form of 10 to the power n r plus un. I'll tell you. Like earlier we did, I told you that a number, say this one, can be equal to 753 into 10 plus 8. But this same number I can express as 75 into 100 plus 38. So sometimes oscillator method can be multiplex oscillator. Some oscillation method can be much faster if you can identify that it is actually something into 100 plus or minus something. So it is actually, so this is in general, you can call that a block of, here block is 2. Here we made a block of 2. So 79, this one. So 10 to the power n means that like here, 10 to the power, here is 10 square. 10 square into 75 plus a block of 2 block of unit. This block, so therefore multiple oscillator is the Vedic method to create smaller integer t is equal to m plus r plus r is the resistor and un is the block. So m is multiplex oscillator of un. It is the nth order multiplex oscillator. Multiplex oscillator is a quicker method for testing divisibility using blocks method. It is a method to determine the required m given a number capital N and this again and D ending in 1379. The nth order of multiplex oscillator m can be found in the following calculator. Here again, I think by given by D is sufficient, not n. We have to remove this. Achha, consider this actually algebra you do not do. Same algebra holds here, like in simplex or simple oscillator. For divisor of the form, like we did earlier for 19, 29, and so on, 199, 299, 39, we could take oscillator as 20, 30, 40, etc. Instead of these simplex oscillators, we may also take 2, 3, 4 as multiplex oscillator and take 2 digits at a time. Let us check whether this big number is divisible by 299 or not. Here, second order oscillator is 3 because where? Why? I'm not writing all of the expression because 299, sorry, 99 is equal to 3 into 100 minus 1. So since it is minus, oscillator is positive oscillator, and 3 plus 3 is the oscillator, multiplex oscillator of order 2. Order 2 is not order 2 because it is 2 numbers of zeros are there. 2 numbers of zeros. We proceed oscillator by this thing. We first cut 2 at a time. From the right. See here you did sparse method. So 2, 1961, we need not do only sparse this last one, that is sufficient. So it is 21961 plus 55 into 3 is this one. Again we do 221 and 26. Again we cut 2 at a time. Here it was not required actually, this sparsing of whole thing is not sparsing, only this part is sparsing. So again we do it and 299, thus it is divisible. This big number, see how fast it is collapsing. The whole big number is divisible by 499 or not. We cut it like this and do this thing into 5. This becomes, again we cut last 2 digits. So this is this into 5, this part. Again we have cut last 2 digits. This one, again we do this and again. It came back to 499. That is it. The question is clear? It is called multiplex oscillator. Now continue with multiplex oscillator. Here you find 401. 401 is equal to what? Now 4 into 100, something into 10 to the power something, plus or minus another thing. Plus or minus 1, sorry, plus or minus 1. So something into 100. If it is plus 1, my oscillator will be obviously it will be negative. But how much it will be? This 4. So it is minus 4 is the oscillator. So what we do? Here we again cut it like this. This one, cut it here. Minus 4 into minus 4. 4. That way, we always do it, and in this thing is not divisible, so it nothing. This is so it is whole things are not. Now this one, it is third order because there are 3 zeros. 6 into 1000. So there are 3 zeros. So it is third order, and oscillator is positive because it is minus here, and oscillator is 6. So it is plus 6. So I do 3 at a time. This plus this into 6, this much. Again do 3 at a time. This much, this plus 6 in 599. That's indivisible. This big number is divisible by 7 into 1000 or not. 7 into 1000 plus 1. So that means its oscillator is 7, third order oscillator because 3 zeros. Oscillator is 7, but it is negative because this is plus 1. So you do subtract. So this one I cut into this part. Again we do just cut it like this. This one, let it come to here. Again like this, we cut it here and then come to and then here you do this cut and becomes 0. That is, whole thing is all these things are divisible by 70 billion. For negative oscillator, the criteria is either 0 or divisible. Now I come to some repeat 9 easy. Like in case of 9 and 11, what we did, it was so easy. Here also, in case of multiplex oscillator, the similar looking numbers also can be very easily found out. A multiplex oscillator are 1 in case of all repeat 9 number, but depending upon what is the level of order. So it is second order. In case of 99, what we do? We group into because 99 is equal to 1 into 100 minus 1. So its oscillator is positive and its oscillator is 1 only. So you don't notice that. Earlier, in case of 9, what we did? We added all these things. But here you are not adding directly. Adding all these things result in divisibility by 9 or not. But adding in group of 2, that is required here. Because it is 99 has 2 zeros, something minus 1, or 2 9s. You can say 2 9s. So you have to do it group into. So these things is divisible because all these things are added to 99. Similarly, this is 999 or not. So you have to group into 3. Its oscillator is 1, but in group of 3. So because it has 3 digits. So here we do not consider oscillator because like in 9, what we do? Like in case of 9, we added all these things in group of 1. I mean, you notice it. Here in group of 9, group of 2, group of 3, group of 4, and so on. Here in group of 4. So this is about repeat 9. So the numbers of 9, according to the numbers of 9, we group. According to the number of 9, we group. Simple. And then nothing more than that. Nothing more or less. You don't have to consider all the oscillator. But what I meant to say, for completeness sake, that this coming from basically it is coming from the same oscillator, but it is don't notice the oscillator. Similarly, divisibility by a hollow number. Hollow number, in case of 11, we didn't find that there are 0 numbers of zeros, but there can be more numbers of zeros. There can be 101, 1001, 10,001, and so on. So this is in case of 11, what we did, alternate plus and minus. Here also we do, but grouping is different because there are 3 numbers of zeros. 3 number of zeros. It is 3 number of zeros is there. So its order is, you can say that after 1, if the 3 digits are there, then you can group. Not zeros may be 2 here, visible zeros, but actually there is 1 more 0 because of which that is coming, is considered. So here you do this one, like this. Alternative plus and minus. So 229 is not divisible. Whole this thing is divisible by 1001. So this is again we do groups of 3. Plus and plus, plus minus, 0. So it is divisible. The whole thing is divisible by, again, that 10,001. So here there are, after 1, there are 4 digits. So 4th order oscillator, anyway, it doesn't matter. Now it is 4, so it will group into 4. Here, like this. From right, mind it, not from left. Never group from left. We always group from right. So we do like this. So all these things, we find that zeros is divisible. Hollow numbers are special cases where nth order multiplex oscillator is -1. Thus, the process leads to alternate addition and subtraction of digits grouped in n, like what you did in 11. Here also, note, repeat 9 numbers of special cases where nth order multiplex oscillator are 1, which leads to simple addition in groups of n digits, like what we did in case of 9. I very clearly, so that you remember whatever I discussed, I also wrote it so that it is. Now, there can be multiplex oscillator for others which are factors of those ending number, I mean, the straightaway number. Like, I have to do now the divisibility by 857. It is sometimes difficult, sometimes it is easy to find. 857 is actually 7 times 857, find that is 5999. So therefore, third order, why third order? Can anybody tell why I am telling that third order oscillator is 6? Why I am telling not otherwise? What is called third order? Why fourth order? Why I am telling what is the order? Huh?
Third order is because you are multiplying with 3 digits. I mean, 3 zeros will be there.
Yeah, yes.
1000 into 1000.
Right. 5 into 1000, 5 into 10,000. Sorry, 6 into 10,000 here. This is actually what I doing. Sorry, 7 into 7. Sorry, I mean this is 6 into 7. So 6 into 1000 minus 1 is 599. So third order because of the 3 zeros. Third order, and this is 6 because it is 6 is being multiplied, and it is positive because this is negative. So similarly, you can say always say this fourth order is 7. So divisibility by 2,333. Divisibility we do by 2,333. So we can do it. Divisibility by 421. This is actually, it is coming for 421 into 19 is this one. So this one always. So therefore, these all are factorized such which are multiplexly closer to 10 to the power something in a multiplex way. We found that these can be factorized. So those factors of all these things will have the same principle as this one. So this is this one exercise on divisibility. Find whether the number this is divisible by each of 199, 101, and 299. Find whether the number this much is divisible by 667, 1667, and test divisibility whether this is divisible by 927. These are the exercises. Now, yes, I end here. But I ready to take the 15 minutes are there, so ready to take any questions from any level.
Gautamji,
Yes.
this oscillator method is interesting, but as the number of digits increases, uska add karna, subtract karna with the multiplier becomes challenging. इससे अच्छा है कि directly you can use our division method. Straight away you find out whether it's divisible or not, right?
Division is will be longer.
No, shorter. It will be much shorter. Like for example, if I look at 101 with the nickel, which is closer to the base, right? So nickel method, I can use it and straight away find out whether it is divisible with no reminder.
So that depends actually. What is the formation of what is the different given numbers are there.
But what would be the use of this approach? Why do we have to say whether it is divisible or not? When do we use this concept?
We use it in various contexts. See, as I told, you learned another procedure. Now it is up to you that which procedure will you use in what context, isn't it? See, 19. You made it very easy or not? In case of 19, we found it quite easy that instead of make it something, divide something by 19. Okay. You divide something by 19. Will it be easier than dividing the digit and subtracting 2 into that, subtracting this thing, adding this thing?
Guruji, one small doubt. Oscillator of 21. Can you please explain once little?
21.
You are 21 into 9 and 189 and 19 as the oscillator you are taking.
No. In case of 21, how to do? 2 into 10 plus 1. I consider this one. So its oscillator is negative and it is 2. That means oscillator is 20 minus 2.
Minus 2.
Oscillator is minus 2. Yeah.
Sometimes you have done 21 into 9 and 189 you have taken.
Oh, I told you that suppose I do not know what is negative oscillator. So in that case, you have to do very big, like here also I have written 21. Yes. So it is 91. Either say plus 91, plus 19, or you take minus 2. Okay, it's minus 2. In case of 21, either you take minus 2 or take plus 91. Because 21 is coming as 2 into 10 plus 1. Here it comes 19 into 10 plus 1. And 19 into 10 minus 1. So plus 19 is the oscillator for 21. No. But do not use that. In case of ending in 1, better to use negative oscillator than positive oscillator.
My question is why we are multiplying with 9, 21 into 9. Why? 21 into 9 we are doing. Why can't with other number?
No, because something you have to end in 9. No, something 10 into 10 into something we want minus 1.
Oh, got
that
it.
means it is ending in 9.
Okay.
Okay. And here it is ending in 1. So when we find something is ending in 1, it is better to use negative oscillator. But in case of 7, ending in 7, you can have alternative. Either you can multiply by 7. Suppose
7.
In case of 7, it is positive 5, or it is this negative 21 and 7 are same thing. 17 is 7. Either it is plus 5 or minus 2. And the interesting thing, this 5 minimum positive and minimum of negative add up to that divisor. 5 plus 2 is 7. Here also in case of 19, in case of 21, it is 19 and then we have 2. So 19 plus 2 is 21. In case of 13, we could have used 4 or we could have used minus 7. Nobody will use minus 7 obviously. So it is 4 plus 7 is not minus 7, minus 9. 13. So that will always will get in case of 17. In case of 17, either you can use 12 or you can use minus 5. So 12 plus 5 is 17 itself. I had the routine in the slide, but it is not there now. So that is the idea.
धन्यवाद.
So this is about the divisibility. Anything, any question about the previous ones? Previous.
Gautam ji, can I
Okay.
add one thing?
हाँ.
Gautam ji, namaskar, Babu bol raha hu. I
Namaskar,
just
namaskar.
wanted to add that somebody asked why we should go for this oscillation method. Please correct me if I am wrong. The use of oscillation is normally you don't do this divisibility calculations, you don't come across. But then you at different stages of a high-end research or some other area, you do it. At that time, this method which is put into the computer logic, it saves a lot of time of the computer and then gives
Right.
the result very fast. So that is the bigger use of this method and bringing the Vedic philosophy. The Vedic philosophy is being brought here. How easy we can do some of the mathematical calculations, cutting down on the time and space. Hope I'm right.
Yes, yes. Yes. It is the, as I told, Vedic mathematics actually is teaching you alternatives of everything.
Yeah.
See, in the childhood, we did for composite number for 2 and 5 and then 3, 9, 11, but we skipped 7 and 13. And then what happened? The more objectionable is that now somebody will tell something and will write a paper on this, but it is already available. I found that so many papers are so many papers are being written because neither the paper judges know that it is already there, and the person is also maybe he has learned from somebody Vedic mathematics. Somebody learns in childhood. Somebody like child student who came from this Vedic Vedic mathematics school, who learned and went to a school and then propagated it further. And this person thinks that, okay, I have done it already. It is not. This is wrong tendency. But many of these things can be written as a paper, then it will be accepted and people, oh, wow, this person is very expert in mathematics and did all these things. So therefore, it is better to know that these are already there. So this is another idea to spread Vedic mathematics, so that we have to first know which is available in our Vedic mathematics. Then only you write paper on this and get your name and fame on this paper worldwide. No. So somebody did paper on this right to left, somebody did paper. Because this is written on this book, this Vedic mathematics book. Earlier we. How many people purchased that book?
I bought that book. Yeah, I bought that. I have it.
This book.
Yeah, same. Krishna Swamiji.
This method, the right to left calculation with multiply and adding, if they carry, this is already there in this. And somebody wrote a paper, and it is in the international journal, it is accepted. So this is has to be taught from childhood so that people know that this is already there. So then they can object that no, it is not there. How can it be the paper is there? And he becomes a paper setter, when a paper selector there. He'll object, no, this is not your original work because it is already there. So that is the idea of studying basic mathematics. All these procedures, somebody may write easily, somebody may write on anything of that. The division procedure. So here we are actually, division is done in the very first go. Here itself, as I told. This is the remainder, this is the quotient. Then I start adding what are the deficiencies. Here it is in case of deficiency is negative, so it is start adding negative. So this way. Okay. Here also, we start adding these deficiencies. We first divisibility, remainder and quotient and remainder part are separated, and then we add this one. Start adding these things, and then do. So
Okay,
these are
I
the
think,
ideas. These are the.
Gautamji, if you permit, we'll go for Pradhana and then continue our discussion and clarification of doubts, if any.
Okay. Okay.
Okay.
Yeah.
Thank you,
Oh,
Ji.
sorry. Actually, just I'll take one more minute. 1 minute. Actually, this is actually thrown in this one. Maybe that. So, so for completeness sake, that they should understand that actually this is all we need cover. That I will take maybe 2 minutes. Second level, I put it inside this. So there are some geometry also. You found there. So this actually, I found that the basic mathematics also, all the hexadecimal numbers can be used, 16 as a base, are equally applicable. So that we found. Somebody may go through it. This one, Pythagoras theorem, you know, there are not many difficult proofs are there in Pythagoras theorem. Here is a very simple proof I found in some basic mathematics book. That so it is like to prove that a square plus b square is equal to c square. Means in a right angle triangle, the individual square is equivalent, sum to is equal to the hypotenuse square. This is actually this one. So this is given a square. With a suppose this is this triangle is given to me. One triangle, and this is B and this is A. So I complete a square like this with BA everywhere, BA. And then we see also I in these points we connect. Then it can be proved that this is also 90 degree and these are also obviously 90 degree. Then we found that this is C square obviously. Now each of them area is half into AB. These are half AB. This is also half AB. This is also half AB, and so on. The 4 numbers of half ABs. Now we found that the whole thing is A plus B whole square. So we found that this is A plus B whole square. And you see that whole thing is a addition of all these triangles plus this inner side. So therefore, A plus B whole square is equal to 4 numbers of all these things, 4 numbers of all these into half AB. Plus C square. And this itself is A square plus B square plus 2ab. So we find that this 2ab part is cancelled, and therefore a square plus b square becomes c square. Is clear?
Okay,
Thank you. No, sir.
okay, let's go for
Okay.
Pradhana. Ramesh garu.
That's it. Yeah, okay. Harihi Om. Swasti prajabhyah paripalayantam nyayena margena महिषाः गो ब्राह्मणेभ्यः शुभमस्तु नित्यं लोका समस्ता सुखिनो भवन्तु काले वर्षतु पर्जन्यः पृथिवी सस्यशालिनी देशोऽयं क्षोभरहितो ब्राह्मणाः सन्तु निर्भयाः अपुत्रा पुत्रिणः सन्तु पौत्रिणः अधना सधना सन्तु जीवन्तु सरदां शतं सत्यं वद धर्मं चर स्वाध्यायान्मा प्रमदः सर्वे भवन्तु सुखिनः सर्वे सन्तु निरामयाः सर्वे भद्राणि पश्यन्तु मा कश्चित् दुःखभाग् भवेत् ॐ शान्ति शान्ति शान्तिः ॐ पूर्णमदः पूर्णमिदं पूर्णात् पूर्णमुदच्यते पूर्णस्य पूर्णमादाय पूर्णमेवावशिष्यते ॐ शान्ति शान्ति शान्तिः सर्वे जना सुखिनो भवन्तु स्वस्ति
ధన్యవాదములండి. Now let's go for జనగణమన. చలా చిట్టుబాబు గారు.
जनगणमन अधिनायक जय हे भारत भाग्य विधाता पंजाब सिंधु गुजरात मराठा द्राविड़ उत्कल बंगा विंध्य हिमाचल यमुना गंगा उच्छल जलधि तरंगा तव शुभ नामे जागे तव शुभ आशीष मांगे गाहे तव जय गाथा जनगण मंगलदायक जय हे भारत भाग्य विधाता जय हे जय हे जय हे जय 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 हे जय हिंद
జై హింద్.
जय हिंद
ధన్యవాదములండి. చాలా చిట్టుబాబు గారు.